Welcome to SanfordFlipMath. This is AP Calculus. We are continuing to work through the Finney, Demana, Kennedy Calculus book. We are in Chapter 6, which is about differential equations, and the main thrust would be solving those differential equations. And the focus for this video is in 6.2 about antidifferentiation by substitution. Sometimes referred to as u-Substitution, and that's mainly just because u is the letter that's commonly used for doing this. And so I just, first of all, one of the first things that the section does is to kind of remind you of some rules, and I'm going to remind you that we've dealt with this list back from Chapter 3, and this is the list of derivatives. And by doing antiderivatives, we're going the other way. So the idea is like antiderivative of cosine is equal to sine, etc. Okay, so I'm not going to spend a lot of time on that, but I do want to draw your attention to this list, which is on the left side is from page 322 from the Finney, Demana, Kennedy book. And this is pretty much the same thing, and what this is doing is it's kind of a blend of some of the properties we've already talked about. Like, for instance, here's that idea that if you're doing an integral and you have multiplication of with a constant in there, you can pull it out front, and there it is. If you were doing antiderivative of a sum or a difference, you can do antiderivative separately, and that works. Okay, it's not distributing, but the idea is similar to distributing. Okay. This is on page 322, and I will have a copy for you in class of this list, just so you can have one handy, but it's in your book. It's not that deep. And again, just to draw your attention to a couple other issues here. Here's the power rule. Add 1 to the exponent, and then you have to divide by the new exponent. And just a quick reminder that if it's just 1 over u or 1 over x, then that's really a natural log situation, and to get that to work for positive and negative numbers, you have to do an absolute value. Okay, so most of this is really the same as this. It's just going the other way using the proper notation for antiderivatives. Now, one other thing I should probably point out, and that's that the antiderivative itself is also referred to as, yep, there. Sorry about that, got a little distracted. So a definite integral is when you have like limits of integration from 1 to 2, or you're finding a specific area. An indefinite integral is also known as basically antiderivative. Okay. Well, the big focus in this section is on what's referred to as u-Substitution. And the idea, what this is for situations where a chain rule happened. So in other words, when you have a function inside another function. Okay, so some nested functions. So basically what it's for is undoing the chain rule. Okay, chain rule is for derivative. And this is the undoing version of that. Okay, so here's an example. Now, we've actually seen something like this already, and we talked about this a little bit in class, but here's the idea. And I'm going to use it on something that we kind of already know what to do with, and then it'll get uglier. Okay, so think of this function. This has a 3x inside a cosine x. Okay, so we already know that what's supposed to happen is, as I do antiderivative of cosine, I know I took the derivative of sine. The 3x had to stay in there. And then what I ended up having to do is, I know that if I take the derivative of this, I'm going to have this times derivative of the inside thing going on. So it times 3. And there wasn't a 3 here, so I have to divide by 3. And then plus c. Well, this is how we've been doing it for the last few days. Okay. Well, I want to take the same problem, and we're going to change it up a little bit. Okay, so cosine of 3x again, dx, and I know that this inside part is like a function inside a function. So off to the side here, I'm going to say u equals 3x. I'm also going to say the derivative of that derivative with respect to x, derivative of u with respect to x, is 3. Now, I'm going to play around with this a little bit and solve it for dx. So if I multiply by dx and divide by 3, I have du over 3. Okay, so this is kind of all side thoughts, and then I'm going to rewrite this function, the integral antiderivative of cosine, and instead of writing 3x, I'm going to write u. Instead of writing dx, I'm going to write du over 3. Okay, now because this is pretty much all multiplication, maybe you could argue that it's division too. I can bring that 1/3 out front, and this becomes cosine u, not cow or cow, cosine of u du. So now what I'm going to do is the antiderivative of cosine of u du. Well, I already know what this is, but again, here's that idea of antiderivative of cosine of u. Well, that's just sine of u plus c, okay, or you could think of it as what did I take the derivative of, okay? Well, I must have taken the derivative of sine, so this is going to be 1/3 times sine plus c. The only catch is that I need to replace the u back with something with x if it's just antiderivative. So 1/3 sine of 3x plus c, and we're done. Now that's probably overkill for that. Okay, now worth noting that these two are the same thing. Worth noting that, so that again, that was probably overkill for that, but there are other problems that get more interesting. Okay, so for instance, let's do another. Okay, so new example. We're going to do the antiderivative of x times the cosine of x squared dx. Now, the thing to notice here is, again, I have a function inside of a function. Okay, so I'm thinking that's probably u. Okay, so it's the inside function that's going to be the u. Now, the other thing that you need to notice is that when I do du dx, well, that's 2x, and notice how the derivative of the inside is kind of here. Now, technically, it's not 2x out there, it's just x, but the 2 I can handle. The 2, you know, is just a constant multiplier, a factor that can be multiplied or divided as I need to. So, but the heart of 2x is there. Okay, so the issue again is I have a function inside of a function, x squared inside of cosine, and the derivative of x squared kind of is present. That's the issue. So that's how you know this becomes an integration by u-substitution problem. Okay, so doing what I did before, I'm going to make a replacement for x squared, and I'm going to make a replacement for dx. Well, in order to do that, I need to know what dx is equal to. So again, I'm going to multiply by dx. Okay, and then I'm going to divide by 2x. So this becomes du over 2x. Okay, so going back to my original problem, I'm going to say antiderivative of x cosine of u, and instead of writing dx, I'm going to write du over 2x. Okay, so this x and this x divide out. I'm going to treat this 2 on the bottom like a 1/2 out in front, and this becomes cosine of u du. This is something that I can do the antiderivative of fairly easily. Again, antiderivative of cosine is sine, and I need a plus c. And the only catch is now that I need to go back and replace the u again with what x is, so x squared, and that's it. Okay, so that's antiderivative with u-substitution. All right, well, let's do another example, and I want to do it a couple of different ways. Okay? Ta-da! All right, so first thing I'm going to do is I'm going to go back to like a chapter 5 approach. Okay? So remember that squared, so this kind of looks like a power rule-ish kind of thing, but not quite. Okay, so remember squared just means times itself. So, all right, so when I do this, this is going to be 4x squared plus 12x plus 9, and that's whole thing with respect to x. And this is an antiderivative I can do just kind of term by term. Okay, so antiderivative of 4x squared will be 4x cubed over 3, 12x squared over 2, 9x plus c. Okay? So I'll simplify this one more step just because I can. Okay, and there we go. Now, that wasn't hard, and you know, I just need you to see that the whole u-substitution thing kind of works. Here I have a function inside of a function. So this is 2x plus 3. So I'm going back and doing the same exact problem. I just want to do it a different way to see if, just to see how things shake out. Okay? So 2x plus 3, I'm going to call that u. So the derivative of u with respect to x is just going to be 2. So dx solving is going to be du over 2. Okay, so I'm going to redo this antiderivative, and 2x plus 3 squared, so u squared. And instead of writing dx, I'm going to write du over 2. And again, I'm going to pull that fraction out in front. And so this just becomes 1/2 times, well, the antiderivative of u squared will be u cubed over 3, and then a plus c. Well, this is pretty much done. The only issue is, what was u? 2x plus 3. Well, over 3, well, I'm going to write this instead as 1/2 times 1/3 is 1/6. Now, here's the joyous fun. Are those the same? Because that's the question, right? Are those the same? Now, worth noting that the c value might be different because of all the multiplying that has to happen, and there was no constant on the end of the first one. But I can tell you that at least initially, if I just cube that front term, now really this is 2x plus 3 times 2x plus 3 times 2x plus 3. Just cubing this first one should be 8x cubed, and then it ends up getting multiplied by a 1/6. So that is 4/3 x cubed, and there'd be some other stuff, and I don't really want to do all the other stuff, but that at least matches the first term. Okay? All right, let's do another. All right, well, this one's worth doing. Okay, first of all, what the heck does that mean? So let's start out by writing this a little. This is kind of like that trig notation, you know, when sine squared really means sine of x squared. Well, this is what that means. Okay? All right, so now next up, do I have a function inside of a function? Okay, I can't just do the antiderivative of natural log of x to the 6th and just go to the 7th power over 7 and then do the antiderivative of x and call it x squared over 2. You cannot do a quotient, the antiderivative of a quotient by just doing the antiderivative of the numerator and denominator, just like you can't do the derivative of a quotient by doing the derivative of the top and the bottom. You can't do it. It doesn't work. You have that whole quotient rule, ho d hi minus hi do ho over ho ho, and all that. Okay? All right, so we're going to do some u-substitution. Now, my thought is that that looks like the inside, and it's being raised to the 6th. Well, let's just kind of make a couple notes here and see if that makes sense. If that's true, then the derivative of u with respect to x should be 1 over x. Do you see a 1 over x in this thing? Well, actually I do. Here is the over x, and I could certainly make that a 1 times over x. So the derivative of u is present. Okay, so let me solve this for dx. So I'm going to multiply both sides by dx. I'm going to multiply both sides by x. So dx equals, in this case, x du. All right, so making some substitutions. Okay, so what I end up with is u to the 6th over x times, now dx is now x du. And then the x's actually divide out. And I'm left with u to the 6th du. the antiderivative of a power then is, so this is going to be u to the 7th over 7. Okay. And at this point, I just need to put that u back in, so ln of x, so natural log of x, to the 7th power over 7 plus c. Now you can leave it like that. That's all good. If you kind of like that ln 7 like this, and if you want to put a 1/7 out in front, that's fine too. I mean, there are options here. Okay. Thinking one more. Now, I haven't really said much about write down the example and then you go to work and pause me and all that stuff. I haven't said that in a long time, so let me just remind you that that is a huge, huge, powerful way to do this. Okay. So, as we go to this next example, write down the example. Hit pause, and then work it out yourself. Then see if we match, or if we're at least on similar tracks, okay? Okay, so go ahead and hit pause. Sorry, I was having my Dora moment there. Are we going to across the bridge, or are we going to the castle? Across the bridge, across, or to the castle? Yeah, no, she sits there waiting. All right, so looks like a function inside of a function. I'm going to call the u that inside part. And then let's just see what du looks like. Derivative of 1 is 0, derivative of negative x is negative 1. So dx ends up being du divided by negative 1, which I'm going to write as negative 1 du, or just negative du. Okay. Now, if you didn't hit pause before, hit pause now, and then see what you can do with this. Okay, so I'm going to keep going. 1 over u squared. Now, in place of dx, I'm going to write negative 1 du. Okay, and again, this becomes, I'm just going to rewrite the form. I'm not doing an antiderivative now. I'm going to bring the negative out in front. I'm going to write this as u to the negative 2 du. That's a power function. That's something I know how to deal with. I just add 1 to the exponent and divide by the new exponent. So I still have my negative. Add 1 to the exponent. Divide by the new exponent. Plus c. I'm going to clean this up a little bit. So the negatives divide out. This becomes u to the negative 1 plus c, also known as 1 over 1 minus x plus c. Did we match? Oh. All right, well, I will tell you that a lot of times the thing that hangs people up is algebra. Okay, so let me do another one, and we're going to just play with algebra. Okay, so again, now if you see what to do with this, if you have an idea, hit pause now and do it. Okay, so what I'm going to do is I'm going to rewrite this, first of all, into a form that makes it a little more easy to identify what's going on. Okay, so I'm going to put the dx on the end, and this is 1 over sine squared 3x. Now, and I don't think this is obvious yet. This maybe is obvious. Okay, now, again, there's a cosecant squared derivative. If you remember, the derivative of tangent is secant squared. The derivative of cotangent is cosecant squared with a negative. I don't see the negative here, but that's easy enough to take care of. So the function inside of a function deal is right here. Okay, so u equals 3x du dx equals 3. Dx is going to equal du over 3. Okay, so doing some substituting here. This becomes cosecant squared u du over 3. I'm going to move the 1/3 out in front. So all we've done is done some algebra, some pre-calculus-ish algebra, in order to rearrange this into a form that we can actually do the antiderivative of. Okay, so again, the antiderivative of cosecant squared is negative cotangent squared. Excuse me, it needed to have a negative involved. Not cotangent squared, just negative cotangent. Okay, plus C. And the only thing that needs to happen here is I need to change the U back to, and let's make that negative out front. The U needs to go back to 3x. Okay, so just a quick little confirmation here that the antiderivative of cosecant squared is negative cotangent. Excuse me, sorry to cough right in your ear. Here it is, cosecant squared. Or if you prefer, right here. Okay, that negative wasn't there, so it must have canceled out from a negative that was over here. Okay? All right. So again, the quick version of this, the quick synopsis is when you have a function inside of a function that would have come from a chain rule, then uSubstitution will help you kind of put things back into autopilot for doing an antiderivative, so that way you can just kind of follow the normal template. Okay? All right, well, that's all I'm doing this time, and thank you for watching, and I appreciate you hanging with things. SanfordFlipMath, I guess we're all done. Bye.